Hi, this is fourth lecture in the module on deterioration of cementitious system. In this we will cover fire attack, abrasion and erosion. We already covered how durable systems could be, and sulfate attack, biofouling and biogenic acid attack, frost and freeze thaw attack, alkali silica reaction and shrinkage and creep. And now we will focus on these three mechanisms: fire attack, abrasion and erosion. Now this is two example. I am going to show you some pictures showing how buildings and other structures get affected by fire. You can see that the entire building on the left side is engulfed by the fire, and on the right side also it is a World Trade Center, and that led to significant damage. Entirely the building was completely damaged. So fire can lead to significant damage. Here is picture showing what really happens, or different stages of fire attack. As you see on this, when the first picture top left shows a slight spalling of the surface, you can see slightly rebars over there, and in the second picture, which is the top right image, picture B, it shows bottom reinforcement is now visible. That means the entire cover is lost, and the picture C shows both layers of bottom reinforcement. That means more the concrete, the fire has attacked more and more of concrete, more concrete is removed, and then you can see bottom reinforcement totally uncovered. And you can see here, as I am looking at this picture, you can see here the reinforcement are also like kind of deformed, in this significantly deformed, because now the rebars are directly exposed to the high temperature. And then in the picture E, you can see bottom reinforcement even falling down completely. So it is no more able to use. So the point here is significant damage can be induced by this high temperature due to the fire. Now this is another picture of a bridge where actually there was a tanker or a truck with the source of heat was solvents burning under the bridge coming from a truck or lorry on the bridge. So you can see that significant damage, even not only for the buildings, even other structures could be exposed to fire. And here this is an example which shows how a crazing and spalling looks like. Crazing is like initial cracks, map cracks, which you could see on the picture on the left side, and on the right side you can see that entire cover is now delaminated and it is spalled, exposing the reinforcement. Now let us see a little bit more detail what happens when the concrete is exposed to fire or elevated temperature. Why I am saying elevated temperature? Mostly it is because of fire only. Okay. Now let us see in the beginning, this picture here, in the beginning you see both the upside, top and bottom of the element is at similar temperature, that is 70 degrees Celsius, and as fire damage happens, the temperature is raised up to about, when it is up to about 120 on the other side of the fire, and at the side of the fire it is at about 1000 degree Fahrenheit. You can see some localized spalling, like some region gets spalled here, and which can happen in about 30 minutes. And then as time passes, at about 1 hour, you can see some significant loss, and some of the rebars gets exposed. Okay. And as the time reaches like about 2 hours, that is 120 minutes, you can see that more and more damage happening, and the rebar itself is now buckled. You can see here the rebar itself is now buckled, means the rebar gets directly attacked by, and it starts losing its properties, and also the concrete element itself starts deflecting or deforming. So all this combined effect, you can say that there can be significant damage to the structural system. Now, let me go through very briefly through the text on the right side. So, what happens? Fire affects concrete in extreme ways, some of which are listed below. Uneven volume changes. Let us say if you are talking about temperature difference at one side and the other side it is much higher, then definitely there will be cracking and buckling and other sorts of distortions can be visible on the element. Now, another mechanism which can happen is spalling of the rapidly expanding concrete surface. So, the concrete expands because of the high temperature and it spalls, especially where the temperature is very high, as it was shown in the bottom 3 images on the left side. And what also will happen during this time is the aggregate also can expand and burst. I will show you some pictures later on some of the aggregates how it can expand because of high temperature. And moisture, another thing which is very main important thing is moisture which is available inside the concrete will rapidly change to steam or water vapor when the temperature increases, and which will exert significant pressure onto the surrounding concrete, and then which also leads to bursting of concrete into small pieces. Now, another mechanism is the conversion of cement mortar into quicklime at when the temperature is above 400 degree Celsius. Now, on top of all this, reinforcement also loses its tensile capacity because the temperature is high and it loses its most of its good properties. So, that reinforcement cannot take any more the tensile loads, and so again the structure starts deflecting. And other mechanism is once the reinforcement is exposed, that will also try to expand, and it expands at a larger rate than compared to the expansion of concrete, and which also leads to significant spalling, buckling and loss of bond. The steel concrete bond is also lost. So, these are all different type of damages which can be induced during a fire attack. I am going to show you these things in especially the moisture action, the item number 2 which we were talking in the this item number 2. I am going to show you how this moisture attack happens. You can see here on the picture on the top left, there is a heat flow through the porous medium. So, concrete is essentially a porous medium. So, heat flows into the concrete from the outside, and then there is a vapor migration which happens. The moisture which is available inside the concrete will migrate outward like this, as it is shown here. It will migrate outward, but what happens is this migration process, during this process there a zone of saturation starts forming slightly away from the surface of the concrete. In other words, there is a condensation of water vapor which happens at a particular zone depending on the porosity of the concrete and pore structure of the concrete, but then that zone of vaporization we call it, and it eventually gets saturated. That zone gets saturated as you see here, and a moisture clog is formed, and then that leads to building up of vapor pressure especially at that region. So, in other words, you can see here this graph with this graph here, which is basically showing what happens, that showing that the vapor pressure, you can see here, this is the point where the highest vapor pressure, and the pore pressure is very high, and that significantly high pore pressure in this zone, which is the moisture clog or the saturated zone, that will push the concrete outward, and which is what we call as spalling. So, this is the typical mechanism on how the moisture content inside the concrete will lead to a buildup of pore pressure and then eventually leads to spalling of concrete. Now, spalling due to large pore and pressure. So, we discussed all these points, increase in pore pressure at saturated form. Yeah. Okay. Now, just to show graphically that the change in the pore pressure and how that. So, you can see here this curve is the temperature, this is the surface, this is on the right end of this graph is the surface and the left end is as you go into the concrete. So, this is the surface region and you can see the pore pressure is very low in the beginning. Now, let us go to this graph. Now, here you can see temperature is slightly increased as compared to the first one. So, 1, this is 2 and this is 3 and this is 4. Okay, now here you can see that a slight buildup of pore pressure is happening and then here you can see again it is increasing significantly high and now this increase, the temperature is further increased and the pore pressure is also very high. So, this is the region which we called as saturation zone or the moisture clog, and here you can see again significant increase in the pressure. Once the spalling happens, that pressure is dropped. So, at this stage before the stage 4 spalling happens. Now, one more thing, this just to show that how it happened. This is from an experiment which was conducted in Sweden by Robert Jansson, and you can see here I found this thesis very informative in this case of fire attack. And now you can see this is the inside surface and this is the region, the bottom is the region which is spalled, and so this is the region which we are calling as the moisture clog. So, you can see a lot of accumulation of water or moisture in one region, and that is leads to building up of the pressure and which eventually spalls the concrete near the cover. Now, this is an example of a lab experiment on a field specimen. There was a fire attack in a tunnel, and they took the specimen to the lab and did another fire test, and the moisture content was maintained at the same level as it was in tunnel, which is about 4%, very low moisture content, or we can say very dry concrete. And however, in this particular experiment they could see about 140 mm of concrete was spalled, and as you see in the picture here, you can see significant spalling, rebars are exposed and also they are deformed. These are all what happens, and once the rebars are exposed and deformed, it cannot really have the structural strength as desired, and the progressive spalling that basically that depends on how long the fire exposure happens, and it is basically showing layer by layer removal. In other words, initially some spalling can happen, then further the new surface gets exposed, and then the temperature rise in temperature inside the concrete is more, and which eventually leads to progressive spalling. And typically the duration could be longer in case of tunnels, because it is like a closed system or a long structure where once there is a fire, it is not like a building where you have windows, doors and open space where the heat is dissipated, but in case of a tunnel the heat is contained inside, and it takes very long time to dissipate that heat. So, fire attack could be very severe in case of tunnels and such structures. Now, what happens to the concrete or the stress strain behavior of concrete due to elevated temperature? You can see here this graph shows the behavior from about 20 degrees Celsius to about 800 degrees Celsius, and you can see the first three, it is about 20 degree which is ambient, and then 100 and 200 degrees Celsius. Not significant change in the property, we can say, at that stage. First three graphs, for practical purposes we can say they are more or less same. Now, when you reach 308, the triangular markers here, this graph, that one you can see that there is a significant decrease. So, something happens at about 300 degrees Celsius, and after that you can say that the graph is significantly changing by reduction in both the modulus, that means the slope in the initial region, and also in the compressive strength, that means the height of the graph or the peak of the graph, both are actually decreasing significantly. So, point is, once the temperature is above 300 degrees Celsius, then the concrete starts losing its mechanical properties. Now, so what does that mean? If the concrete starts losing its mechanical properties, then we have to do probably replace the concrete or do significant repair work, so that the structure can retain its capacity. Now, what happens to the thermal conductivity of concrete? That can also decrease at elevated temperature. As you see here, when the temperature is, let us say, from the ambient conditions, which is here, and it goes to about 800 plus degrees Celsius, you can see there is this about, if this is 1.5, this is about 0.6, almost 50% reduction in the thermal conductivity. So, that is also a significant change. Now, factors what govern that govern the fire resistance of concrete. What are the factors which govern the fire resistance? Until now we were looking at what are those changes because of the elevated temperature, and now let us see how to address those things, so that we will have less change. First thing is thermal conductivity, and then specific heat of concrete, that means how much heat can be absorbed by the concrete before it penetrates into the concrete. Okay. And what are those? Moisture content of concrete matters, and then a mineralogy of the aggregate matters, and then the type of cement hydration products also, and of course the structural design. What it means is the size and shape of the structural element, and what are the design features for dissipating the heat energy also. Now, aggregates play a significant role on the fire resistance. What are those roles? Like the ability of the aggregates. See, aggregates constitute maximum volume, is about 75 or even 80% of this concrete could be aggregate, considering both fine and coarse aggregates. If they can absorb the heat without rapidly increasing the temperature of concrete, it is very good for fire resistance. So, absorption of heat by the aggregate is something very important. If they can absorb more heat then per unit volume, then that is very good. And aggregates with high thermal conductivity are poor performers. What that means is, if there is a little bit of fire or the higher temperature on one side, it will be easily conducted into the concrete. That means the internal temperature of concrete will also rise very easily. So, that is not very good. Now, what is good is with high specific heat, that means if they can absorb heat per unit volume, they perform very well under fire, and that is dependent on the mineralogy of the aggregate, this specific heat capacity. Now, what are the good performers and bad performers or poor performers in case of aggregates? Anything which we say as with really reasonably high pore high porosity, then they will perform better when you talk about fire resistance. So, for example, you can say limestone, it is definitely more, it has more pores as compared to granite stone, which is granite is not a good performer in case of fire. You can see a picture at the bottom left, where granite during a fire test, the picture here it shows like flakes of granite or knife like edges are also visible on this. That this is actually a granite stone broken into pieces, so under fire. And now on the right side you can see a flint before fire, and this is after fire. The same aggregate pieces are broken into, and one word here is interesting to note: splits violently. They break violently into smaller pieces. That means if we use flint or granite in concrete, they can also break like this inside the concrete. So, it is not just the cementitious part which is breaking, but the aggregate itself also can break into pieces. So, we have to be careful we may not be able to change the aggregate for depending on what is available, we will have to use those aggregates. So, what we have to do is what are the other ways by which we can protect the concrete structures which are vulnerable to fire damage. So, one way of doing that is incorporation of plastic fibers. They can help in relieving the pressure, because this spalling happens because of the pressure buildup, as we discussed earlier, the moisture clog, and then it increases the pore pressure and then leads to spalling. So, here is the picture on the left side, you can see region the left side of the picture is the cover concrete. So, in this about if you go up to here about 50 mm, up to about 50 mm thickness, there is no plastic fibers visible, but at beginning there was plastic fibers. So, you can see here some hair like fibers visible in that region. Now, what it means is during the fire attack from the left to the right, as the temperature increases and reached about 160 degrees Celsius, the plastic started melting, and it leave that whatever the space occupied by the plastic fibers, they help in providing pathways for the water vapor to to go out of the concrete. That way prevents the building up of the pressure inside the concrete. So, this is a good practice which people used to do, especially for tunnel linings and structures like that. So, picture on the right side shows this on the right side there is a fiber bed, that is a place where the fiber was kept originally, and after exposure to a fire or an elevated temperature, you can see that the fiber started flowing. That means the molten fiber, molten plastic, it started flowing and started occupying another space. So, when it starts flowing into the other space available in the concrete, that means this path is now available free for release of pressure. So, this is how the plastic fibers can help in controlling fire damage or minimizing fire damage. Now, permeability and rate of temperature increase, permeability of the concrete and the rate at which the temperature rise of concrete happens, they also influence spalling. Higher the concrete permeability leads to less distress. Why? Because then you have more pathways for the heat for the water vapor to get released from the concrete. Now, higher strength, typically high strength concrete will have more compact microstructure, especially when you use silica fume or low water cement ratio or any other SEMs which we use today. They might have a more compact microstructure which can lead to explosive spalling under high temperature, because they do not release this when they do not provide pathways for the water vapor to move outward. So, then eventually the pressure build up significantly and eventually it leads to explosive kind of spalling. So, we must ensure that there is a, if we are talking about a fire, if the structure is probably vulnerable for fire attacks, then we should make sure that there are sufficient ways by which the heat does not get into the. So, there are a lot of coatings available nowadays which prevent the rise in the temperature inside the concrete. So, that is probably one way to go for, because if you are talking about lowering the permeability or increasing the permeability of concrete, then the problem would be there will be durability related issues. So, maybe the better way would be to use good quality concrete, but at the same time provide a coating which will kind of function as an insulation for the function as an insulator, and it will prevent the temperature rise inside the concrete even if there is a fire attack. Now, let us say you are seeing a structure where it is already experienced a fire damage, and we need to know what was the maximum temperature which was experienced by the concrete. So, how can we do that? By looking at the color change in the aggregates, we can identify what is that maximum temperature, and this is possible because of the presence of iron bearing compound in the cement and aggregates, and iron undergoes different degrees of oxidation at different temperatures, leading to different colors. So, I will show you a graph on the next slide, and so this different relative color differences can be an indicator for the temperature, the maximum the peak temperature which the concrete was exposed to. As you see here, if you see a pink color, then that we can say temperature was probably somewhere in this range, that is about 300 plus, and if the color changes towards red, then that is about up to 600 degrees Celsius, and then if it is grayish in color, then 700 to 800 degree, and if it is buff color, then it is about 900 degrees Celsius. So, there are charts like this which shows or helps us to determine what was the peak temperature, and now once you know the peak temperature, then you can say what is the probable decrease in the modulus of elasticity and the compressive strength of concrete. So, as I showed here, how the stress strain behavior will be different if you go for this this increase in temperature here, and the stress strain graph significantly changes, or stress strain behavior changes. So, all this is required, we need to know what was the peak temperature, or then you have to go and do take cores or take specimens from the concrete and then do some testing. But the point here is you may not be able to get cores because they are all now spalled and cracked. So, getting cores also may not be a good idea. So, you have to have these tools available to be able to relate to the color, and then what the mechanical properties could be, residual mechanical properties could be. Now, let us look at abrasion damage. What is abrasion? It is basically wearing of surface because of repeated rubbing, rolling, sliding or frictional or attrition processes, and repeated action of lightly loaded rubber tires or foot traffic, even in the form of dusting, loss of surface texture, etc., and polishing. So, these are all ways by which we can define what is wearing and how it is manifested by localized crushing, scratching or attrition, and in case of heavily loaded steel wheels. So, where do we see this? Most often it is visible on either industrial flooring where you have heavy vehicles moving, or on highways, road structures where you have vehicular movement. That is where we see this abrasion most often. And let us talk about a little bit what happens, the process. The first step would be you have an intact mortar or a concrete with aggregate, these round round circles you can see they are all aggregate, representing aggregates. And then on the second stage here, what you see is some portion at the top is lost, and then you have aggregates are partially exposed. Now, in step 3 you have some aggregates which are completely lost, and then this this surface starts moving downward, the abraded surface, the front keeps moving downward, and then more and more of such aggregates are lost, and the entire. So, you can see here the progression of the abrasion in concrete structures. So, first the fine particles are lost, then you have small aggregate particles gets exposed, and then more and more aggregates gets exposed, and eventually you have significant loss. Now, this is a picture on the right side very clearly shows this. You can see that aggregate particles are lightly visible, and this can also lead to potholes. Now, this is a picture showing where significant amount of aggregates have have been removed. You can see here in this portion it is only the cement paste is removed, but here you can see significant amount of aggregates are also. So, this is the initial stage, this is the initial stage, and this is the final stage or later stage. Now, what are the major factors affecting the abrasion resistance of concrete? So, compressive strength, water cement ratio and hardness are the three major factors which affects the abrasion resistance. You can see here on the picture on the left side the percentage loss by volume, it going here, and as the compressive strength of the concrete is less, you have more and more percent loss. Now, on the two graphs on the right side, this is abrasion erosion loss. Again, all these studies are done based on the amount of material loss. So, here you can see water cement ratio changing from 0.4 to about 0.72. So, as the water cement ratio is lower, it is better, that means less amount of material is lost. And here you can see as the water cement for the same water cement ratio, if you draw any line over here, you can see how different aggregates perform, with limestone showing maximum damage and quartzite, trap rock and shirt showing less damage. So, definitely water cement ratio plays a role, and the aggregate and its hardness plays a role, and also the compressive strength of the entire concrete also plays a role. Okay, now how to ensure good abrasion resistance? Use high compressive strength concrete, use lower water cement ratio, use harder aggregates and well graded sand and instead of fine sand, okay, and then larger aggregates than smaller aggregate, and make sure that the concrete is very well cured, especially that will ensure that the top layer of the concrete is hard enough, because when you talk about abrasion, it is mainly the top layer which matters. So, you have to ensure that the top layer is of very good quality and avoid lightens. You can see here what is lightens. It is like a thin layer of weak layer of concrete on the surface due to bleeding, excessive bleeding of fresh concrete, you can see. So, these kind of things indicates that the near surface will have very porous structure. So, that will lead to significant abrasion damage. Now, erosion and cavitation, especially these are happening in hydraulic structure, because you are talking about water body there. So, these are the typical structures where this will happen: open channel, closed conduits, spillways, gutters, aprons, stilling basins, sluice waves, all these are part of hydraulic structures. These are some, you can see here significant damage on this. So, these are type of structures, many part of the hydraulic structures where there is a flow of water along with debris, etc., you can expect a significant erosion and cavitation. Now, how this happen? Erosion, there are three actions in this. One is abrasive action, the second one is cavitation, and then there is also a chemical action. Abrasive action is because of the presence of debris in the water which is flowing, and the cavitation is because of the intense local stresses which are formed due to the air cavity formation and collapsing of those air cavities, and we will discuss that detail later. And then chemical action is basically dissolution of the hardened cement concrete which can happen. So, all these gives in combination gives this erosion damage. So, what is the abrasive action? You see on the picture here, there are huge rock boulders which are flowing present on this is the bottom portion of a spillway. You can see large boulders. So, they actually abrade on the concrete surface and lead to damage, as is shown in the picture on the right side here. You can see a large particle hitting the concrete, it locally damages the concrete, and when multiple actions come, and then eventually the entire concrete surface get eroded or abraded and and get damaged. This is a cavitation plus abrasive action, because all this water you might also have either debris or sand particles. So particulate material will be present in the concrete, and if that is the case you can have abrasion. Now let us see what is cavitation. Mainly this happens when there is a change in the shape, or if there is an irregularity in the concrete surface. So because of this irregularity, so for example here as you see on the picture on the top right, you can see there is a small region which is a air void formation, or in a vapor forms in low pressure, which leads to formation of the air bubbles, and then eventually some of the air bubbles will coalesce and then become a large air bubble, and then what happens eventually is that they start imploding, like as you see here in the 3 and 4, this air bubble, because of the again water pressure, it collapses in this, from here it collapses into 2 smaller air bubble, and then there is a jet of water which is hitting the concrete surface, as is seen on the 4 case 4 here. You can see here there is a jet of water which is hitting locally, and that kind of action leads to significant damage to the concrete, or cavitation damage. So again the same thing what I just discussed, I am putting it in text. Cavities will form in running water whenever the pressure in the water drops below the vapor pressure, and when these bubbles collapse under high pressure, they do so with great impact, and as the bubble collapse, the space gets occupied by high velocity water. Extremely high pressure is generated in a small area for a fraction of a second or momentarily, and then cavitation damage is more pronounced when large number of very small bubbles coalesce to form large bubble, which then collapse as shown in this sketch over here. Now these are some examples showing how big this cavitation damage could be. You can see some people standing here and the size of the damage, and this is also a large significant damage. Here also you can see significant damage on a spillway, and this is a a very huge such damage experienced in this Glen Canyon Dam in Arizona in 1980s, and that significant damage, you can see people standing here, and the size of this damage is so huge. Now this is another example. This happened in 2017, sorry, it's 17, and there was a spillway. You can see the dam structure here, and there is a spillway here which was failed, and you can see how the damage started. Initially there was very small damage here, and then it eventually led to significant damage, and the entire spillway, the bottom portion of the entire spillway was completely lost, and this is a repair of that structure. You can see the entire spillway was removed and then now rebuilt. Now it is looking good, but lot of money spent. So if so you can see here the damage started from here and then led to huge damage. The entire spillway was lost. Now some sketch showing the details on how this cavitation can happen. You can see here there is some erosion at the bottom portion here, and then cavitation. This is happening because of this irregularity on the surface over there, and the natural roughness of the surface can also lead to cavitation. And here you can see a change in the surface profile that also lead to cavitation. So any uneven surface or irregularities on the concrete surface which will lead to cavitation. So even if it is very small, because of the high velocity of the water, it can lead to colossal damage. So it is something very important, especially for hydraulic structures, to be taken care. And this graphs on the right side also shows, sketches on the right side also shows offset into the flow. So flow is from here, you have a projection of the structure here that leads to flow of water like this, and which leads to formation of cavities like this, and which eventually lead to damage in the downside here. So like that, here you have flow and the structure is like this, and there is a sudden movement of water downward, creating a cavity here, and which lead to damage here. So likewise, all this picture you can see surface irregularities lead to significant damage on the concrete. How do we protect concrete structure against cavitation? Especially high strength concretes containing smaller aggregates, and then smooth concrete surface with minimal irregularity. This is the most important thing, I believe, because that will prevent the formation of cavities. And good aggregate paste bond, the aggregate should not get dislodged from the concrete, and hardness is not as important for cavitation resistance unless erosion or abrasion resistance. Now sudden increase in velocity of water should be minimized, but that will happen because of the shape or irregularities on the concrete surface. So if we take care of the smooth concrete, ensure that the concrete surface is very smooth and there are minimal irregularities, probably the risk for cavitation is less, or the probability of cavitation to occur is less. And the purposeful aeration, this is something new technique which have been adopted in many structures nowadays. I can show you some pictures. So this is what how it is. You can see here you are basically pumping air into the water body so that there are more air bubbles, and also introducing steps like this. So you see on the right side picture here, there are steps on the spillways which helps in dissipating the energy, and so that the pressure which is acting onto the concrete is relatively less, and it avoids the damage due to cavitation. So major difference between cavitation and eroded surface: in case of cavitation, surface is highly irregular and pitted, whereas in case of eroded surface it is more or less uniform or more uniform than the cavitation damaged concrete. This just showing another repair. You can see here again they are making sure that the surface is very smooth, because that is the one which is very important to ensure there is no cavitation damage. Hard, strong, but at the same time very smooth transitions, no irregularities should be there. To summarize, now first we talked about fire damage, and so moisture movement, we discussed about how moisture movement happens in concrete during an elevated temperature, and then we talked about moisture clog, which leads to building up of pressure inside the concrete, which eventually leads to spalling at high at high temperature conditions, or especially when there is fire. Mechanical and thermal properties of concrete can get affected because of fire attack, and concretes and aggregates with high porosity perform better in case of fire, because they provide pathways for the heat for the moisture to get released from the concrete. And properties of aggregates and strength of concrete influences abrasion, erosion and cavitation resistance, and shape of the structure and minimal irregularity. These are the two things which we have to really worry about to prevent erosion and cavitation in hydraulic structures. I think with that we will stop today. These are the references used for making this lecture. Thank you.